As many of you know, over the years, I've designed and built multiple submarine robots, ROVs. And so I have an idea of the challenges that are faced by the Titan crew, the Titan submersible that sadly went missing with 5 people on board. First of all, my heart and prayers go out to the friends and family of the people on board. Um, I hate to sound so negative, but I think I've kind of had my suspicions horrifyingly confirmed with the discussions today with various groups. So, SubBrief just came out with just posted a video. He's a very good channel, very informative on a lot of submarine issues, as he's a former submariner himself. And he brought up a number of points I never thought about, actually. I was more concerned about structural integrity, things like that. He did make a very good point that, okay, yeah, you're sealing people in this thing, and it can be an oxygen-rich environment. They had scrubbers in there, but they are putting oxygen into the environment. What if you get a fire? It's a very good question. And he brought up the Apollo accident where 3 astronauts were killed on the launch pad. They didn't even get a chance to go in flight, and they were killed from a fire in an oxygen enriched environment. And that's a very, very good point I hadn't thought of. I've been looking at it structurally. A lot of people on Twitter were saying, oh, they're using a PS3 controller. I mean, come on, what kind of cheesy operation is that? Actually, that's really smart engineering. See, you got to understand, down at this depth, the pressures, to give you an idea of the pressures, okay? So it's probably around 6,500 psi, so pounds per square inch. So little, 1 square inch surface area on the hull of that vessel will be 3.25 tons of pressure. So a little 10 centimeter square patch, you're looking at 52 tons. So basically, park a loaded rail car on an area this big around and hold the weight and don't let any water in. So I mean, if you have a wire going through the hull, let's say you have the wire going through the hull, and you can actually seal around that wire. The water pressure is so high and so intense, it's beyond hydraulic. Most hydraulic operating systems only operate at 2,000, 3,000 psi. This is more than double that. The water will treat that wire as a pipe, as a hose. The water will force its way through that pipe, through that wire, into the vessel. So having a wireless controller is actually pretty smart. It's one less through hull connection you have to worry about, and one less opportunity for failure. Now, they had multiple backups on board, but if that controller fails, how does their backup systems work? We've all used Bluetooth. It was Bluetooth wireless. We know how finicky those can be when you're trying to pair 2 devices. So let's say the controller fails, and okay, you grab the backup controller, and okay, is it pairing okay with the controller, which is on the outside of the vessel controlling all the motors? So I have no problem with the wireless controller. That's actually pretty smart. A lot of people were making a big deal of that, saying it's a cheesy operation. No, that's actually pretty smart engineering, for a number of reasons. Also, bear in mind that even if there was a complete failure of all propulsion systems, they still had I think it was 7 different methods of getting back to the surface. So they had, and some of them were quite ingenious, in fact. So they had the usual. They did have airbags, which at that depth, this was the problem I ran into in my course 3, in my robotics course, where we are doing a case study where we are designing an ROV submarine to go down to 10,000 feet. Now, the Titan and the Titanic is almost 13,000 feet. So even if I had my sub built today, I couldn't get down there because I hadn't designed for that depth. It's an unreal depth. So at that depth, even with my ROV sub, for example, you know those CO2 cartridges you can get for things like whipping cream dispensers or your CO2 paintball guns, for example. Those containers do not have enough pressure in them at 10,000 feet to, if I opened up that tank and tried to fill an airbag under at that depth, water would force its way into the pressure tank because the water pressure is greater than the gas pressure in the tank. So how do you fill an airbag at that depth? You can't. So what they do is they have a bunch of backup systems. They have, for instance, ballast, just dirty old steel pipe with rocks or scrap steel or whatever in it. So they had several different systems. The first one, the primary one, was electrically operated, and a little electric motor would basically pull the pin and drop these steel pipes. And you could dispense with probably half a ton worth of ballast weight that's holding you down, making you sink. Quick guess. I don't know what the specs are because I haven't been able to find any of that. They also had a hydraulic system as well. Now, this works very well for hull pass-through connections because hydraulics are fluid power. So you have less opportunity for leaks. It's still a hole through the hull, which can cause problems. But you don't have the water trying to force its way through the hydraulic tubing because it has to fight the hydraulic pressure in the lines, for example. Okay. Anyway, regardless, they had a manually operated hydraulic pump that would also release a second batch of ballast weight. Bags with ballast on board. So you ditch those, you're now buoyant, you start to float. They had a third system, which was really smart. They called it roll-off ballast. And basically they had two shelves on the outside with pipes, round pipes, that were filled with rocks, scrap steel, whatever. And so literally they're held in place by gravity. That's it. And so they get everybody inside the sub over to one side. And so the sub tilts. And when it does, this rack is now downhill. The pipe literally rolls off and you just ditched all that weight. Now it's heavy on this side because of the weights on this side. Those now roll off. You've just ditched hundreds of pounds of ballast. You are now positively buoyant. You'll start to ascend. They had, what were some of the other systems? Anyway, they had a bunch of really, really smart systems because at these pressures, it's near impossible to say fill an air tank. We're talking super hydraulic pressures. How do you deal with that? How do you gain buoyancy? And you basically can't. And these are the challenges that I ran into that I specifically brought up in our case study, trying to design a submarine ROV to go down, say, 10,000 feet. That was the goal. So these are the problems that come up. So these guys are going a third deeper than what I was trying to get to, okay? So this is incredibly dangerous. Now, the clincher that came up in the discussions on SubBrief's video, someone brought it up in the comments, and I hadn't thought of this. I had concerns about the carbon fiber hull of the Titan. But I've never worked with carbon fiber pressure vessels. I've never used carbon fiber scuba tanks, for example. I have no idea of their reliability, if they've had failures or whatever. I can tell you this. What little I have worked with carbon fiber, I can tell you that when it fails catastrophically. It shatters. Okay, so think of it like glass. Okay, you can put glass is actually surprisingly strong, but once it fails, it's instant. It shatters. Carbon fiber is very much the same. It's not at all like metal, which will bend and then fail. It'll buckle. Carbon fiber will just shatter. So the hull on the Titan was made out of carbon fiber. So I had questions about that because it was the only one I was aware of that had a carbon that had such a pressure hull. So as a result of the ROVs that I built and whatnot, I wound up becoming a part of this online group of people around the world who build submarine ROVs or personal subs. Now, no names mentioned, but there was one guy who he had it professionally designed, a carbon fiber pressure hull for his sub, and apparently it was designed for 6,000 meters, so now we're talking like way deeper than the Titan was intended to go. Now, fortunately, this person tested this hull. So they threw it out deep in the ocean on a tether, presumably, and just let it sink. And that's how you test the hull, is just drop it down to the deepest part of the ocean. And apparently it made it down to 3,000 meters before the hull catastrophically failed. So this kind of confirms in my head, sends off all kinds of alarm bells. It horrifies me to say this, but this kind of confirms my suspicions in that these carbon fiber hulls may be the issue. I don't know of anyone else who has built a composite hull like that for extreme depth. This is the only other case that was brought up in that group that I've ever heard of, and it failed way like half of the design range, which should send everybody's alarm bells up. You should sit back and stop and ask questions like, what is going on here? Why did it fail there? That's not even close to the design pressure. Not even close. So what's going on there? Another comment down on SubBrief's video, which I hadn't thought of until I read it. And the moment he said that, I'm like, uh-oh, he's right. Because he said, well, isn't carbon fiber really strong in tensile strength? How is it for compressive strength? The instant he said that, I knew he was right on the mark. Let me give you an example. This is not carbon fiber. I've got some carbon fiber here, but I can't find it. This is fiberglass, but it's the exact same principle. It is extremely strong in tensile strength. But in compressive strength, there's literally nothing. There is no strength. It's flexible. It's floppy. The only thing that keeps it rigid is the resin epoxy. So when you're making carbon fiber sheets or a hull, you are impregnating it with liquid plastic, which then hardens into a hardened plastic. It's resin epoxy. So they had a 5-inch thick carbon fiber hull. Now that's really thick, and that resin epoxy would be really strong. But the carbon fiber is actually useless because it is trying to compress. The pressure is compressing the hull. This is why when I brought up the question about carbon fiber scuba tanks, which is kind of a more recent thing, I've never used one. I have no idea the reliability, but it dawned on me afterwards, it's irrelevant because carbon fiber scuba tanks are dealing with tensile strength. It's the pressure trying to pull the carbon fiber apart, not crush it. So that is irrelevant. What we're looking at here is literally you're trying to withstand the weight of a freight train on the hull using only the strength of resin epoxy. Apparently on the hull, they also had sensors all over the hull that was basically monitoring the health of the hull and giving updates and reports. Here's the catch. I don't understand and cannot see how that would possibly make any difference whatsoever. Let's say the hull started either shrinking too much, like more than predicted, or the sensors picked up cracking or crackling inside the hull. We're talking fractions of a second between the start and finish of catastrophic collapsing and failure. There's no response time. The pilot wouldn't have a chance to hear an alarm and like, ooh, drop ballast and let's start ascending. It's not there. Quick guess, maybe 1/10 of a second as a quick guess. At those pressures, it would be instant. And in some ways that's, I don't know, cold comfort, for lack of a better word. Their deaths would have been instant. They would have been dead before they even knew it. And it's extremely dangerous, and they knew that going into this. All those people, unfortunately, the one guy was very young, 19 years old. But it would have been instant. You need to test this. I get it. All deep submersibles are experimental craft. I totally agree. But it's a pretty cheap experiment to seal it all up, put a really long cable on it, drop it to the bottom of the ocean, let it sit for a while. Let it sit for a couple of days down there, and then reel it back in. It's not that expensive to do that kind of test. And apparently such tests never took place, which, that horrifies me. Because the reason I built 5 submarine ROVs is because the first 4 sank. I was learning as I went, and I was learning all the ways that you don't do this. And perhaps they would have discovered that, maybe a carbon fiber hull isn't the greatest design. So it is with much sadness. I have much respect for these people and much respect for what they were trying to do. So that's just my quick analysis. I hate to what's the word, discourage hope, I guess. But I have to make the prediction. I think we're going to find that when they do find it, they will have found that the hull actually imploded. And this is raising a lot of questions for myself as well from an engineering standpoint. I hadn't gone down this road of trying to build a composite hull, for example. I'd always used either acrylics or metal. That's all I've ever worked with. So anyway, this is definitely going to change everything, I think, for tourist submersibles going to deep water and whatnot. Although there isn't that many doing it already. There was a couple of Russian ones, but they've been retired years ago. So anyway, I don't know. I'm conflicted about whether to even put this video out or not, but I will probably post it.